So, in this problem, we're going to explore what ways we might be able to extend our definition of what is a Turing machine and how that changes the concept for us. Specifically, Dr. Hyper Turing Machines, Inc. is selling a variety of different kinds of Turing machines. So, we have our basic old Turing machine that has a single one-directional infinite tape. You can go off as far as you like to the right side of the screen. And it has a single tape head tracking where you are. This one will cost $9.99. But it's got some more advanced variants too. So we've got a two-directional infinite tape in the bi-infinite Turing machine. And this means our tape head can go as far as we want to the right, or as far as we want to the left off into the negative indices. We could also have an infinitely scalable Turing machine. In this one, we have the same old tape, but we have as many heads as we want on top of this tape. So here I've illustrated 3, and you can imagine a transition function that takes in the input at all of these different heads, reading from all of them, and then potentially writing at all of these different heads as well. But again, a bit more expensive than the standard version. Finally, we have a quad-core Turing machine. And this one looks pretty standard. It's got tape just going off to the right side and has a single head on that tape. But it has 4 copies of this tape. And so we can do all of these simultaneously, and again might have a transition function that considers reading from each one of these tapes and writing to these individual tapes, but treating them separately. So the question is, are these just some sort of marketing gimmick that they want you to spend more money on a Turing machine that isn't actually worth more? Or is there something actually valuable here that you might be able to do with these Turing machines, but not with one of the standard that you saw earlier and that were cheaper? If your friend was buying one, what would you advise? Now would be a good time to pause the video and think to yourself, what sort of a problem might you be able to solve with one of these more advanced Turing machines that you couldn't do with a typical one? Well, as you were thinking of that, hopefully one of the things that came to mind was the Church-Turing thesis. And that said that any computation that we could do with any sort of computing device in our physical universe can be carried out by a Turing machine. And when we made that, we were really just thinking of a plain old Turing machine. And so, presumably, if these other Turing machines are doing computations we can describe, we might be able to follow their instructions, they are computable within our universe, then they should be able to be computed by the standard Turing machine as well. Another way to view this might be as compilation. That if you wanted, you could probably write code to simulate one of these more advanced Turing machines on your own in whatever your favorite high-level programming language is. And then, as we've seen in lecture, there are ways to take that code and compile it down to instructions that could work on a normal Turing machine. So, advanced Turing machine to code to regular Turing machine. Clearly, we could run them there as well. But, so all that should be sufficient, but it's not as fun as actually seeing directly how these other Turing machines can be simulated. So if you want to stay and see more of the details, feel free to keep watching the video, and we'll look at each one in a little more depth than just the fact that we can simulate any physical computation. Let's start out with the bi-infinite Turing machine. So here, what I'd like to know is, can we take a Turing machine with only a single directional infinite tape that only extends off to the right, and with that, can we simulate a Turing machine with a two-way infinite tape, effectively? Well, let's chuck everything over to the right, because we're not going to be able to extend to the left. We want to find some way to have both of these infinite sequences only going past 0. And the easiest way to do that could be to do something like intersperse them and put a 0, then -1, then 1, then -2, then 2, and so on. That we put the negative numbers in between the positive numbers. So both of them can climb to -infinity and to infinity respectively, but they're only doing that going towards the right. If we were to do computation on this Turing machine, for every time we might just have gone left or right on the previous Turing machine, here we'd need to go left or right twice, potentially with an extra state, because if we wanted to get from 2 to the left, we'd jump over -2 to get to 1. However, we can do that in Turing machines with an extra state in the middle as mentioned, and so this is entirely feasible. There are a few other details to work out. For example, if we were to provide as input to this Turing machine some string, well, by definition, this will just be placed down on the Turing machine in the standard indices. And so if we want to start using it as if it's a bi-infinite Turing machine, first we'll need to do some initial step of stretching the string out and inserting a blank symbol between each of the different symbols of our initial input. Again, however, we can do this. And to finally clean things up just once more, we said earlier that we'd go left twice or right twice in order to get to our new position. But that doesn't actually cover the one case where we might need to wrap around if we're at the left edge and we're going left because we're counting down, and we need to start into the negatives now. We need to recognize somehow that we're on the very left side, and so we need to start going right to go back down further. And to do this, the easiest method is to have some sort of marking symbol extending our alphabet and saying this is the left side of the tape so that the Turing machine can recognize and start moving in the other direction from there. From this, it's not a specific 7-tuple definition, but it's hopefully in enough detail that you can see pretty precisely how we could simulate such a Turing machine with our standard model. Now let's move on to some of the others. So our infinitely scalable Turing machine. We can go back to a regular tape, no complications there, but here we want to have a lot of different tape heads. And fundamentally, if we want to simulate this, we're going to say we can only have our standard 1. And so we're going to need some other way to keep track of what all these other tape heads are doing. Specifically, the easiest way to do that is going to be to put them in the alphabet. And so for every character on the tape, rather than just storing the character itself, it is the character and also whether or not the red head is at that position, whether or not the blue head is at that position, and whether or not the green head is at that position. Now, if we want to simulate a single step in which we read from the different tape heads, and we write to them, and we transition our state, we can read over the entire tape, and as we're doing that, learn where are the different positions that these tapes are in. And more importantly, what is on the tape there? So where should we be transitioning to? Once we've done that entire thing, we know what we need to do, and we can go back and again find those positions to write the correct values and do more. This might be a little bit slower, but again, we can simulate any computation that we were previously capable of doing with just our single head moving around and acting as all three or all however many with additional colors and additional markings if you needed to. Finally, let's look at the quad-core Turing machine. This one feels rather complex. We've got 4 entirely different tapes. But again, there are tricks we can use to simplify this and effectively put it all on one tape. So let's start by squashing them together, putting them on a tape. We'll need some way to differentiate where the bounds are. Where does a tape end? Where should it be extending off into blank symbols? Us Turing machine builders like to use hashes here. And so you can imagine these as extra symbols on the tape. Now, we've got one long tape with 4 tapes within it, and we can see where each tape begins and ends. if we needed to add something on to one tape or another, we could simply stretch it out, push all the other tapes further out, and make more space that should have been a blank symbol. There's another minor detail that, as you've seen, we have now 4 heads on this same tape. But for that, we really just have the exact same problem as we had with the previous Turing machine. And so I imagine we can do the same sort of trick in which we mark each of these heads, and then we're able to walk between them to simulate the processes of these different heads now on different tapes, before just on the same tape, but functionally the same by now. So, looking back on what to buy, our normal Turing machine can simulate any of these other Turing machines. It may not do so quite as efficiently. We're not providing any guarantees about how fast these Turing machines would run, but if what we want to do is compute a problem, any of these language extensions is not really necessary. And this just again goes to show how nice our definition of Turing machines is, that it is able to encompass all of these possible additions and just doesn't actually need to be made any more complex than it is as is.